Good afternoon, everyone. Today, it's our pleasure to have Dr. Kelly Brunt with us. Dr. Brunt is an associate research scientist with ESIC and also with the Quires Physics Science Laboratory and NASA Goddard. She received a BS from Syracuse University, an MS from the University of Montana, and a PhD from the University of Chicago. As a postdoc scholar and Scripps Institution of Oceanography, she worked on ice, cloud, and land elevation satellite. These are altimetry data. He's currently part of the IceScan 2 mission and is working on post-launch calibration and validation of the satellite elevation data. Let's welcome the speaker.
Thanks, John. Thanks, you guys. Thanks for coming out. This is just gonna be a lot of fun. We'll show you a new asset that NASA has going for it. It's pretty cool. And the title is meant to just suggest some of the fun at the very end. We'll show you some cool videos about how we're validating this stuff, which is totally the fun part of the whole mission. I want to thank John and Kazi actually for setting this up. You guys did a really, really good job, especially John chasing me down. You'll see why it was hard to get a hold of me. But hey, listen, we know that our ice sheets are losing mass. They're losing mass quite a bit. Basically, our ice sheets are losing mass where they are in contact with both our warming atmosphere and our warming ocean. So it's around the coastlines. And that's pretty apparent here in Antarctica, not here in Antarctica, but here in Antarctica, sorry. And we know this from different assets that NASA has had. ICESat, which John mentioned in the bio, that was operational between 2003 and 2009. We have a massive aircraft campaign, IceBridge, going on. Just finished up deployment in Greenland, and it's getting ready to go to Antarctica via Australia in coming weeks to months. And of course, GRACE, the gravity satellites, excuse me, measuring changes in mass. So we've known this. It's even more obvious in Greenland. Greenland's got a much, you can see the seasonal signature of Greenland, but it's actually far more straightforward, unequivocal sort of downward trend with respect to mass. And again, these things are happening along the coastlines. They're especially happening in these really large fjord basins, Jakobshavn over here, Helheim down here. So this area right here and this area right here, very obvious, huge losses. And we'll talk about the fjords again in a few minutes. So with all this mass change, obviously the concern there is we're just taking ice that's grounded and pushing it into the ocean system, raising mean sea level rise. This is what keeps our ice sheet type glaciologists up at night. Sea ice is a different story. We've got massive changes in our sea ice. You've of course seen something like this where I think Sinead Farrell gave a talk a couple weeks ago. We're looking at sort of the extent change through time, and there's definitely some interannual variability to that, but the trend is down. This is all fine and dandy, but the more important story is sea ice thickness. What you're looking at here is a really cool animation that took a lot of time to put together. Basically just tracking parcels of ice through time. Time or age of that sea ice is a good first order proxy for thickness. Our really old ice is also our really thick ice. And what you're seeing here over time, we can talk about this for a little while because it's going to run to 2016, I think. But what you're seeing over time is the really white, bright, old parts of our Arctic pack ice are thinning, they're going away. You can't make first-year sea ice, or you can't make 5-year sea ice in 1 year. So ultimately, the loss of that thick, old ice is actually a greater concern to the sea ice scientists than the actual extent. You can see that for the most part, that pack is moving down towards Canada and Greenland. When people talk about an ice-free Arctic, they're not talking about all of it right away, but you can see it's going to be pretty easy to get across the Arctic kind of on the top of that plot up on the Russian side of things. The plot on the right is actually just showing you where we are relative to the original averages for that particular period of time. We're coming up towards the end, and I didn't expect you to remember what the first part of this video looked like, so we'll have a before and after at the end of this. But thickness is a major concern, and obviously as you lose your Arctic ice cover, you're actually changing this is stuff I know it's all basic for you guys, but you're using that sort of cap that keeps the flux between the ocean and the atmosphere in control. You provide more of an exchange and you change global climate. So this is the before and this is the after. That's 1984 on the left, 2016 on the right. Same time of year. I'm not cherry picking. I'm not. This should be apples to apples. And I hope the takeaway is, yeah, we've lost a lot of our real thick Arctic pack. So with those two major concerns, changes in our ice sheets, pushing water directly into the ocean, changes in our sea ice, probably having an impact on global weather. And I actually think that second bullet point, I'm a land ice scientist, so it hurts me to say this, but I think changes in our sea ice are probably more important to us in a more immediate future. But between these two things together, the decadal survey suggested, hey, let's have a follow-on to the highly successful ICESat mission. ICESat, again, was between 2003 and 2009. We need another laser altimeter to continue looking at these changes in the polar regions. So boom, ICESat 2 is a directed mission from NASA headquarters with two measurement goals. There's many, sorry, there's about 15 or so mission level goals, but two measurement goals that are key to the polar regions. Basically measuring ice sheet surface change to less than a centimeter. I was not there when they made that requirement. I'm just the victim that has to deal with it. We'll show you that at the end. That's where the tractors come into play. That's the fun part. But remember that. We need to do this with centimeter level accuracy. That's crazy. Sea ice thickness, that's the other measurement goal for ICESat 2. Basically looking at freeboard of 3 centimeters. That's also a crazy number. Again, I'm not responsible for that. Just picking up the pieces and moving forward. So these are crazy, crazy accuracy requirements, and I'm really optimistic. I'll show you some early results from ICESat 2. I'm really optimistic that we're definitely in line to meet those, which is very cool. And the third part of this is with ICESat 2, which launched last year, and I'll show you a video of that in a second. That'll be wicked cool. Ultimately, we're continuing a 15-year laser altimetry time series that NASA's developed with ICESat, IceBridge, the airborne part of it, and now ICESat 2. So September 15th of last year, we just hit the 1-year anniversary on orbit. That's wicked cool. We launched the satellite. There's no sound here. Don't worry about it. It's your standard NASA video. They count back from 10. And then if you go to see a launch, try to see one in the wee hours of the morning or at night. Make sure to have a reload. You get a good show for sure. This goes up and hits the marine layer, so it kind of disappears for a second and go into a model run. And then it bounces back out. It's kind of weird. You go to these things and you're excited that it's going to lift off, but you're scared, you're excited, you're scared. It's not good for your blood pressure. Ultimately, the big sort of release is when it gets to the second stage. So this video kind of runs out until we hit that point. Super exciting. We were a little bit delayed in launch. I think when I first got to NASA, we were supposed to launch around 2015, and it kept sliding all the way back to 2018. So by the time you get there, there's a lot of people that have been working on this mission. A lot of people in the launch that have been part of ICESat, and we're at the ICESat launch back in 2000. I think it launched in 2003. No, data started in 2003. But there's a lot of time that people have invested in here to finally see this happen, which is really, really cool.
Solid rocket motors.
This video is. At the end of this, it hits second stage, which is great. That's when the full release, you're calm down, you drink your coffee.
Delta will hold on to those motors.
It was exciting. This went out of Vandenberg, California. Everybody thinks of launches maybe out of Kennedy. When you're prograde, you go out of Kennedy, you're kind of going with the rotation of the Earth. ICESat 2 is in polar orbit. There you go, there goes the stage. We're in a near polar orbit. We've got an inclination of about 92 degrees, so we're retrograde. You go off of Vandenberg out of California. Both those prograde, retrograde is in case anything happens, you end up in the water. And that's what this kind of covers. So we've got that 92, we got a 98 degree, 92, sorry, I meant a 98 degree inclination. We're polar orbiting, we're retrograde again, opposite the direction of the Earth's spin. I've just got an ascending orbit there shown in green as you go across the equator. If you're going up, that's your ascending orbit. You can imagine on the back side of this image, things are going from the North Pole down towards the equator. That's the descending component of the orbit. We are at 500 kilometers above the ground, which is really, really cool. And we're getting centimeter level accuracy. Come on. That's awesome. That's amazing. Just to give you a sense of where everything is, so a lot of the low Earth orbit, that includes things like all your sun synchronous, your A-train type stuff. They're at that about that 500 kilometer to 700 kilometer range. Just to give you some other numbers, here's the lunar orbit. The sun is still that way. Discover's that way. James Webb is getting ready to go up in a couple of years. That'll be off that way by a lot. Yeah, I don't know what else to cover on this. I always like the orbit stuff, though. I'm a glaciologist, so getting into the orbit stuff has been a fun component of working on this project. So Atlas is the instrument that's on board ICESat-2. ICESat-2 is the bus, the metal parts with the solar panels and all that good stuff. But the actual instrument that's up there, the laser altimeter, is called Atlas. Atlas is a relatively new type of technology in this vein for spaceborne applications. It's a photon-counting laser altimeter. We basically send a shot of photons towards the surface of the Earth, and we time tag all of them. Our detectors are open, and we're just getting every single photon back against the detector. That includes a signal we sent out in the 532 nanometer wavelength. We filter a tight window around that so that we're not getting that much other stuff hitting our detector, but we still do get ambient green near to that wavelength hitting our detectors. So when you first get these data sets, and I think I have a couple examples of sort of raw type data, you have to filter out, this is my signal, and this is my ambient background. I don't want to call it noise. It's a touch of instrument detector noise, but what I'm really talking about is stripping out the background, the solar background. It's a 6-beam setup. That's really awesome compared to ICESat. ICESat was a single beam. The number that I like to give everybody is ICESat used to send a shot out once every 170 meters. That's about a football field and a half, including a couple end zones. ICESat-2 shoots a pulse every 70 centimeters. That's about 2.5 footballs. So we're going from measuring with units of fields to measuring with the units of the football. So we've got amazing long track data density relative to ICESat-1. We're a 6-beam instrument. Some of that is to get sort of off nadir coverage. You can see how they're set up right here. So we've got 6 beams set up in 3 pairs. Those beam pairs are intended to get a cross-track data density, but they're also intended, those little beam pairs are intended to get us local slope right away. So in steep areas, we can actually get slope and we can get surface change in one measurement. With ICESat, we had to actually get a lot of passes over the same area, get a sense of the local slope, and then grab change out of that measurement. Here we're doing it in one shot, which is wicked cool. I think that's all I have on that. So the measurements that we're actually making, we're measuring just the surface height. We're not doing anything like radar going into the subsurface at all. We're literally just measuring the surface. So you measure the surface of the ice sheet. Let's start on the left. You measure the height of the ice sheet in meters. You change that height. You can measure change. Sorry, with 2 passes, you'll measure change. You're going to have to sort of interpolate that from a long track measure of change to some sort of volume change over the ice sheet. But then the hard part, the really hard part, is to then turn that volume change into mass change. You have to know something about the density of the ice, and that's where the big time science comes in on the land ice side. That's really hard. I've got a slide that addresses that. It's very cool. Harder still, I think. I'm very happy I'm not a sea ice scientist right now. I'm sure Sinead was like sweating when she gave her talk. But here you're going to measure the height of the surface of the sea ice. That's going to include both snow and ice. So having some sort of understanding of the density structure, especially the top of that sea ice, is really important to get at the thickness. So you're going to measure the height of the sea ice, the height of the lead right next door, get the difference, throw in something about density to get at the thickness. So that's, in my mind, a much harder job than what we have for us. Sorry, sea ice. So here are some early results. This is from some work by Ron Kwok out of JPL, and these are 2 sort of seasonal assessments. This is just a freeboard. This isn't quite at that thickness yet. But this is unbelievable to us because of the coverage. And again, we're getting really close to the pole. We go all the way to 88 north and 88 south. That'll become important later. On the sea ice side of things, we used to only go to 86 with ICESat. So this is a huge kind of step in the right direction for coverage and data density and all that good stuff. So these are really good early results. This is just straight up height of the ice sheet. So this is early results for ice sheets put together by Ben Smith and a bunch of other folks. This is great, but again, you want to get to change. So this is height change. This is ICESat versus ICESat-2. So now we're looking at about a 12-year, is that right? About a 12-year difference between the 2 measurements. And you can see, if you look at the center of Antarctica, you can see that 86-degree pole hole instead of the 88-degree. So we're just stuck with what ICESat had to offer. And again, this kind of hammers home the ice sheets are changing again, where they're in touch with both our warming ocean and our warming atmosphere. It's especially apparent in the West Glacier, left Antarctic, or West Antarctic ice sheet, excuse me, the left Antarctic ice sheet. I know there's no reason to call it the West Antarctica or East Antarctica. It's a holdover. Don't ask questions. The left side of that is what we call West Antarctica, all the stuff that's got the color to it. The right side, if you lifted up the hood on Antarctica, the right side of that, the bedrock is much higher. The East Antarctic ice sheet, if it starts to retreat, can actually retreat to high ground and be somewhat saved. The West Antarctic ice sheet sits on bedrock that's fairly depressed below the surface and below sea level, and ultimately, if you start chipping away at that, it has no place to run. That's why we talk about East and West Antarctica differently. East Antarctica, which holds about 50 meters of water equivalent, can actually run to higher ground and be fairly safe. But West Antarctica holds about 5 meters, and I'm rounding those numbers down, but 5 meters of sea level or water equivalent. It can't really run away. So that's why we're extremely concerned about West Antarctica. The NSF, the National Science Foundation, and NERC in the UK have now a joint effort to go out to the Thwaites Glacier area, which is this area right here, because of this very reason. So, and I don't want to persist on this slide. We submitted something Friday for science, and that was actually going from, instead of just height change, that was going to mass change. So we've done the density arguments, we've jumped in there, done everything that we need to do, and we submitted on Friday, which is really cool. I don't want to linger on that, sorry. All right, so ICESat 2 and IceBridge. Where does IceBridge fall into this? ICESat was operational between 2003 and 2009. ICESat 2 just launched in last year, 2018. We've got a 9-year gap in our satellite record. IceBridge has been targeting some of those rapidly changing areas in both Antarctica and Greenland with laser altimeters, but also with radar instruments. Radar that definitely sees into the subsurface, different types of radars. Some of them just look at accumulation. Some of them go all the way to the base. It's really cool. But most people think of NASA as a satellite or a human space travel organization. That's fair. And we're excited to have ICESat 2. That's what you can do in 1 year of ICESat type observations. IceBridge, 2009 to the present, that's basically what you can do in a really, really good coordinated year. This is actually working with the Germans, I believe. But this is what you can do in a really, really good year of IceBridge data in Antarctica. The top is what you can do on the ground, and that's sad. Not very much relative to the satellites, and we'll come back to that. But ultimately, all these things tie together. We're using the ground-based data to validate our airborne, and we're using our airborne data and our ground-based to validate the satellite. So all these things go together, but it's not usually what people think of when they think of NASA. They certainly don't think of tractors up on the top there. So again, IceBridge is linking the two missions. It has these radars on it. This is going to be the last year of IceBridge. We just had a campaign in Greenland. It's almost certainly the last IceBridge campaign in Greenland. They're getting ready to go to Antarctica. That will almost certainly be the last IceBridge campaign in Antarctica. But I want to again impress upon people that IceBridge is more than just a laser altimetry mission. The radars on board that aircraft, we cannot do that type of thing from space. You can actually, I think I have a slide here. You can actually see, I think in a couple slides, you can actually see all the layers, in some cases all the way to the bed. We can't do that type of radar work from space. So in my mind, some flavor of an IceBridge type mission will happen in the future. It'll just be proposal driven. IceBridge was a directed mission, excuse me. I think that there will be some sort of proposal driven effort to have a similar suite going out and studying this stuff. It just won't be IceBridge or IceBridge 2 or anything like that. So again, I want to impress upon people that our change is happening around the edges, and that's how IceBridge is linking the gap between the two missions. It's actually specifically targeting the coastlines. That area in West Antarctica that I showed you was changing the most, but that's how we do it with aircraft. Ultimately, the instruments on board include the laser altimeter. I think that's the green splooch. And then the radars that do different things. They're tuned differently. Some of them just look at the top layers, the snow layer, which is really cool. That's really good for sea ice. For just looking at the little bit of snow that's left on top of the sea ice with a snow radar, that's great. But again, some of them go all the way to the base, which is amazing. And with that data, now you can actually start to, this is what I call sweatshop data analysis. One of the guys at NASA put together all of the radar lines that we had going, not just from IceBridge, but from the same suite of instruments going back to about 1994, and basically started to make a three-dimensional look at our ice sheet. So he's taking all the radar data, tracing the layers. That's hard work right there, tied together with some of the ice cores that have been drilled in Greenland. And there's a handful of those that make it a little bit easier, and they're spread throughout the island. That helps a lot. But from that Brunt, data analysis work that he did, we're able to actually have this amazing three-dimensional sense of the island. We have hammered Greenland with this type of flight line effort. We haven't done that quite so much in Antarctica. To a certain degree, we've done it a little bit in West Antarctica. We got a chance of having a similar product for the West Antarctica ice sheet, but this was an amazing undertaking and only made possible by the fact that we had, at this point, 25 years airborne radar data over this region. That's pretty amazing. So this is the main instrument that they've been using for their airborne laser altimetry. It's called ATM, Airborne Topographic Mapper. Again, with IceBridge, it's been operational from 2009 to the present, but they had been running this altimeter back as early as about 93, 94. It was traditionally a 532 nanometer green wavelength, just like ICESat 2, but what we've done really recently, and I'll show you why in a couple slides, is we've added a 1064 component to that narrow scanning component of ATM. So there's a wide scanning component to it, and then a narrow scanner as well. And the red has been incorporated into that narrow scanner. I don't know why there's a direction of flight arrow. It should be obvious, but if we're sampling this way, we've got two conically scanning lasers on board at different angles. They fly at a height off the deck, only about 1,500 feet off the surface of the glacier, which at times is harrowing. It's exciting. And they fly in an old NASA P3, which is it's a very nice platform to be doing this. A lot of room to walk around and get to all the instruments, kind of service them as needed throughout the flights. So the 1064 channel, what we've known the whole time is that the green wavelength will penetrate the surface of water. Near infrared does not, but green will. From the ice sheet perspective, you put water on the surface, maybe in a melt pond. Yeah, you'll see the top and the bottom of the melt pond, and that's great. We'll get volume estimates of the water masses that are on the surface of the ice sheets. But it's not great if, say, the snow is just wet. What does the green signal do in wet snow? Not ponded snow, but just wet. Now, there are aspects of this that are absolutely wonderful for science. This is one of the first shots we had looking at ICESat 2 data in a near coastal, kind of very shallow bathymetric situation. And look at how we're mapping not only the surface of the water, but the bathymetry underneath it. I've seen traces of the bottom up to about 50 meters in depth. That's amazing. So this is going to unlock a lot of great things for people. You can imagine we could probably map a lot of the Bahamas using this. That's very cool. But again, it's sort of a little bit of a headache for ice sheet scientists. So this was an instrument that we had out a couple years ago, simple laser altimeter that had co-located near-infrared and green footprints. On the left, in the near-infrared, you can see the signal just pinging right off the surface of the pond. This is the background that I was talking about. This is the white of the ice sheet. You get a lot more reflectance, a lot more background count off of that. But I know that you see a little bit of ringing there. That's an instrumentation issue. But for the most part, that signal is bouncing off the surface of the pond. On the right, what you can see is you've got the green channel not just bouncing off the surface of the pond, but I hope you can see it's also tracing the bathymetry. Again, this is great for coastal waters, but what happens, again, let's just say before Greenland was up for sale, the thing that was putting it in the news was that the entire, pretty much 90-some-odd% of the surface of the ice sheet was in a melt state. Every place was kind of above 0 degrees, so that the entire surface was susceptible to melt. What happens in this state with the green laser? So most recently, when IceBridge was out in the field, we went out with them with a hyperspectral imager. Actually, the PI likes us to say imaging spectroscopy instead of hyperspectral. But ultimately, we went out with a hyperspectral imager to get a look at what this would all look white to our eyes. But what we're getting from the hyperspectral is a sense of how much water's in there, so water content, grain size, so that we can then take the IceBridge red versus green altimetry data, the ICESat 2 altimetry data, and this hyperspectral data to say, hey, this was the melt state. We expect that green laser light might have been ringing around, especially relative to the near infrared. So the idea is ATM would have a near-infrared surface. Maybe just below that, they'd have a signal from, or a spread out histogram of the signal associated with the green. And we could tie that to maybe a grain size issue or a melt issue in the hyperspectral data. So I just got back from Greenland. Thank you, John, for being patient. He was bugging me for abstracts and titles, and internet up there was pretty bad. But it was a really, really exciting time because we had an aircraft, and the lowest aircraft in the photo is a B-200. And it was flying Avars NG, this instrument right here that took these images. This was flying Avars NG for ICESat 2. The top aircraft in that picture is the IceBridge aircraft. It's a G5 rigged up to have a suite of instruments, not quite like the full P3. The P3 is a much bigger aircraft. This had just a snow radar and a laser altimeter on board. But that was flying a lot of long lines that we were trying to mimic. And then the aircraft in between is from a project out of JPL called OMG. Is anybody familiar with that? They're dropping SONS into, and CTD type stuff into the fjords. Remember I showed you in the very beginning, like Helheim and Jakobshavn, those places where we're losing ice big time. And they're dropping SONS into those fjords to get a sense of the temperature and salinity profile and see how that water is chipping away at the bottom of some of our fastest changing outlet glaciers in Greenland. So what's really cool about this is it's 3 different missions with 3 different aircraft in Thule at the same time. It's hard to do logistics in Thule. It's hard to email people from Thule. It's hard to do anything out of Thule. But ultimately, this was super exciting to see all these aircraft in one place looking at the same types of stuff. All right, so I told you that we have centimeter level accuracy and centimeter level precision for ICESat 2. We're starting to show that, and this is how. So basically, ICESat 2 in the polar regions is in what we call a repeat track orbit. We have a different scheme in the mid-latitudes. If anybody is a vegetation scientist or interested in these data, in the mid-latitudes, I'd be happy to sit down for a couple minutes after and talk to you about it. My focus today was supposed to be on the ice. But ultimately, we've got 1,387 unique tracks. And in the polar regions, we're in an exact repeat. We come back and we repeat that track as best as possible. And what you can kind of see, we're polar orbiting. We've got this 92-degree inclination that I talked about before. So we're going to 88 north and 88 south. And what the takeaway from this is that all those orbits ultimately start to converge at 88 north and south. The same number of tracks, 1,387 tracks, have to evenly space around the equator, evenly space around 88 north and south. This is about 40,000 kilometers. The 88-degree circle is about 1,400, 1,300, something like that. 1,400, there we go. So that's an extremely data-dense region for ICESat 2. It's also where all the orbits kind of converge, so it's an orbit-rich area for ICESat 2. So we decided we'd drive it, some of it. So we drove about 20% of this. That ultimately ends up being about 300 kilometers along 88 south. I think we hit something like 275 ICESat 2 orbits in the process. So we're by driving this and dragging along, survey quality GPS, we're getting not only just X and Y or lat and long, but we're also getting a pretty good assessment of Z, of the height. We'll use those heights to make direct comparisons against ICESat 2 heights and see exactly how we're doing. So it's an annual. We'll do about 5 of these, definitely 4, maybe 5 of these. We use 2 Pistenbullies. Those are the same types of things that like groom your ski areas. It's 4 people because there's only 4 comfortable seats. If you were the 5th person, it'd be very uncomfortable. 14 days of driving. It's very frustrating. My parents have a place in South Carolina. It's about 750 kilometers away. If I get up early in the morning, I can be there by lunch. This 750 kilometers took me 14 days. So it's very frustrating. But 10 kilometers per hour. We can't do it all on our own. So we have those blue triangles represent fuel caches. We had 6 fuel caches where the Antarctic program dumped out some fuel for us. So we used about 18 drums, 55-gallon drums of fuel in total. Too much bad music, too many old Slim Jims. And they said, no, it works. Nobody was no one worked that. So in this That sort of so in year 2, we moved that campaign out. Again, just this is and this is the point of we're doing here. Very high. We don't get a lot of snow. There we go. There. And it's on the right. It's done well through the through the bump, but you get these wind-driven, and they end up being pretty firm dunes in the snow, which is kind of cool. So it's it's on my mom's side. Up in the upper left, there's always about 5 to 10 knots, but every once in a while, so 15 knots to 20 knots. Straight. Other thing is basically macro scale, working their way down ice sheet. There's no mountain, so there's nothing shearing it up or skinning it around. For the most part, just kind of bumpers in. And we get there, this is U.S. Air National Guard. These are big skis that allow them to. And some dogs. Very pretty. And I remind people it's just a road trip, so we ain't jumping it. Here's a gas station. Here's some fuel caches set out for us. This guy is actually fixing the vehicle with the whole steering mechanism opened up, but we're moving the whole time because that's a hose clamp holding down the gas pedal. You're probably not going to hit anything out there. Probably not. Just the other Pistenbully. Here we are fueling up, and then this is an extremely nice day. We actually decided to eat dinner outside. This is just a rollout. Second year phone. Sled. If you act up, you had to ride in the sled. This is probably this is from the second year. That's probably my favorite shot of the whole trip. Okay, so some results from here. We had a paper come out last year where we took these data, the GPS data, and compared them against some of the airborne altimetry instruments that IceBridge uses. So ultimately, first of all, the GPS to GPS was just 1 centimeter plus or minus 4 centimeters. That's pretty tight. I'll admit that that's probably a little bit low. There's probably some atmospheric error that we couldn't really shake out because we do what's called precise point positioning, post-processing. We're using each of these 2 GPS receivers against one another. They're experiencing the same troposphere. So there's probably a little bit more error to that than what's there. So for year 2, we did a much better job of figuring out what that is. I think we've added a couple centimeters to that assessment. We did a cool little trick where we drove a short stretch of the traverse in the very beginning, turned around, drove the whole traverse, and then compared our before and after data, 2 weeks separated, to get at a little bit more of that atmospheric component. But the take home is our altimeters are doing really well. So you can get down to about 4 centimeters of bias, which you can work out. You know, you can take that out if you really feel like you're confident in those numbers with a good tight precision. Anything much better than 10 centimeters is really hard to get for airborne altimetry data. But now we just submitted a paper to GRL that actually shows our early assessment of ICESat-2 data products over sea ice, and we're getting about 3 centimeters plus or minus 9 centimeters. So that's the trend, that the plot that you can see right here. We're showing basically all of all 6 beams, which at this point still have what we consider uniform calibration. We're going to work on that for later releases of the data. But this is a first pass. This is basically the first 6 months of ICESat-2 data, and that's the type of accuracy or bias and precision that we're getting. So we're really, really happy with how we're doing. And this is just a ready for publication cartoon of what we're doing. Ultimately, what's happening, is this one? Okay, so this is talking sort of in the future for the Antarctic campaign, but we'll have ICESat-2 data obviously being collected now. We'll have IceBridge based out of Australia for October and November of this year, and then we'll be again on the ground just behind that in December and January of this year. And this is what that'll look like. Basically, the bright green represents the ICESat-2, 2 90-meter separated ground tracks associated with one of the pairs. The cones here, or the circles rather, represent the ATM data, and then this squiggly line here, because we don't drive as straight as those guys, represents the Pistenbully. So we'll have all these data to sort of make that sort of stat comparison, ground versus air versus satellite, which is cool. All right, so this is just a summary slide of things we covered. IceBridge is winding down. It's kind of sad for a lot of people over at Goddard. ICESat-2 just launched, though, so we go from one mission right to the other. These will continue. ICESat-2 will continue this sort of 15-year time series, which I think is super important. These data, this is also a really key point, these data are freely available to the global community. You don't even have to really register at NSIDC if you don't really want to. They want you to so that you can be made aware of updates to that, but there's no sort of, stop to people downloading that data. We'll provide the best record of ice sheet change, period. Like I think from satellite, from a data density perspective, we'll have the most accurate sense of change in the ice sheets, which is unbelievable. And the traverse data that we're using, we've been using this all along to figure out how we're doing, and we do it really quickly, but we're basically, I think this pole hole is one of the best ways to assess how you're doing, especially in the early days of a satellite mission. And that's all I got. I'll take any questions you guys have. Be more than happy to stick around. Thanks for everybody. Larry, I knew it.
Very basic question. It's just a fieldwork question. I noticed the Pistenbully, is that what they're called? One seems to have a beam going out front with I presume a ground penetrating radar for looking at crevasses. And is one more important than the other?
The people inside are more important. No. This was theoretically the lead vehicle. I made the route. I don't want to drive through crevasses. So I made the route. I made it in a relatively crevasse-free region. Crevasses are where crevasses occur where you have any sort of speed variation or any sort of weird relationship with the base. We're in really thick ice that's moving really slowly, and I made sure of that. At one point, the Antarctic program wanted us to go a little farther out on one line and come over, and it was too close to mountains, and by too close, I mean something like 200 kilometers. So I made the route. I put it through a nice crevasse-free region. As the last sort of hazard mitigation, the Antarctic program asked us to bring a ground penetrating radar board on our first campaign, and we don't have to do that anymore. We sort of proved with a white paper with these data and with IceBridge data that this is a very quiet zone, safe for ground travel. But I do like to tell people that the less important people traveled in this vehicle. Good question though. Yeah, ground penetrating radar. Honestly, at 10 kilometers per hour, which was our nominal speed, you can't stop in time. These things are really handy when you're traveling really, really slowly through a super crevassed area. Then you've got a chance. But we were traveling too fast to have that be effective.
I have a question regarding to the ICESat-2, the satellite.
Yep.
And actually you have a very dense observations at
Yeah.
88 degree and latitude. I mean, if northern, I mean higher than 88, do you have any observation? I mean, 89 and 99.
Yeah. So our orbit inclination was. You can only adjust two things. You can just like how high you're going and the inclination, and that has an effect on your ground track print. And our inclination plus our elevation kind of dictated this really nice spaced out 1,387 tracks. If we had adjusted anything a little bit farther towards the pole, our ground track would not have had the same type of map. So we were balancing those two. We can off point up to about 5 degrees without doing any sort of huge damage. That doesn't get you 5 degrees from, not 5 degrees in latitude, sorry, 5 degrees off of satellite nadir. It doesn't get you that much farther, I think. Let me see if there have been times when we've crossed, I can't remember if you can see it here. You can kind of see right here where we've been sort of doing that. That's about the extent that you can get. We don't do it regularly because ultimately we want a repeat track mission over the ice sheets. But that's the extent of it, not too much farther toward the pole. There were talks, especially for the sea ice community, of what would happen if we went all the way to 90. But the map of how it would repeat and the timing of how it would repeat was not advantageous at all for changing the polar region. But good question. If did I get that right? Did I interpret that? Okay.
I was curious, just two quick questions. One, what is your the pulse duration of your laser pulses?
We're shooting at 10 kilohertz. So there is that what you're asking?
The duration time of a single pulse.
Oh my God, I think it's, I think our pulse width is something like, at the surface is something like 1.5 nanoseconds, but don't quote me on that.
Okay.
It's really fast, and we're shooting at 10 kilohertz. Atmospheric folks in the crowd, there is folding. You know, we do get clouds that suddenly appear, you know, intersect our ground. It's easy to pull out, not easy to restack. If that makes sense. At 10 kilohertz means you'll have lots of balls in the air at the same time. But yeah.
And then also, you have quite a few observatories in Antarctica. I'm curious, do you have to turn off your the ICESat's laser when it's flying overhead to avoid
Like
saturating?
the micropulse, the upwards looking stuff?
Yeah.
No, hasn't been an issue. No, I don't know how sensitive our detectors are. I don't know what, I mean, those things go through the atmosphere. So how, I'm wondering.
I would think it would saturate the detectors, the laser pulses.
If maybe in the green, and maybe if you're really lucky. I mean, we're hauling the mail when we go over the top of them, so it would take a good shot. Yeah, I'd worry about the green because we filter everything else out. But at 500 kilometers up, I'm not sure, because those are atmospheric applications, so I'm not sure how far they're when they get a little weak, but not something we were worried about. What we do have to worry about is the other way around. We have to be very careful operationally when we go over things like the International Space Station. So, but I don't think we're too worried about stuff pointing up. So the question was, how stable is the orbit? Is it sun synchronous? We're not in a sun synchronous orbit. We have our own light, so we don't care about the sun's light. Yeah. Yep. So early on, we were not pointing to our RGTs, and that took us a while to figure out. Ultimately, I think we have something like a 600-meter box that we want Lockheed Martin to stay within for us. And they've been doing that and then some. So it's been pretty good. There's a little bit of variation with latitude, but nothing that we don't know, understand, can map out. You know, the flip side is we got into a time recently where we thought, oh, hey, let's burn a little to get back here. But then you just burn. So we just decided let it swing out a little bit outside of the box. But for the most part, the box is something like 600 meters. They want you to be inside that. But we've been much better than that. We've been down at the, sort of the under 100 meters for much of the mission, which is good.
And measurement accuracy at the edge of the ice sheet and center of the ice sheet the same?
No, and that has to do more with slope. So slope is the bigger player there. When things get steep, your geolocation accuracy drops off rapidly. And the edges of our ice sheets are pretty steep. So it's not a function of latitude as it is a function of slope around the edges. And we've got different metrics, different mission requirements associated with steep terrain as opposed to centers of the ice sheets.
I saw the change map.
Yeah.
And some area that's just maybe in the center of the ice sheet is is zero.
Yep.
Zero. How you get that change map? It is what reference you
There's a lot going into that. There's so again, the center of the ice sheet is pretty much a desert. We're not getting a lot of snow there. Ultimately, what goes into that is the biggest thing is a firn density model. So figure the firn is the top layer of our ice sheets where things haven't been given enough time to fully compact under its own weight. So you can imagine the first year's snow, or this year's snow hasn't been covered up. You go down 10 years, it's covered up by a little. You go down a couple thousand years, it's covered up by a lot, but it's still not glacier dense. So we've got firn density to give us a handle on that. And honestly, that's where the real hard part of the science comes from. A couple years ago, there were papers with very differing results on what was going on in the center of the ice sheet. Ultimately, we hope to be able, mostly through data density, through better firn models, better data going into those firn models, we hope to provide a more clear picture of what's going on in the center of the ice sheet and clear up some of the sort of divergent results that were going on, say, 5-6 years ago. But it's hard. That's where the real hard part of ICESat 2 analysis is. Hit it right on the nose.
Another very basic question is, at the center of the ice sheet is only have the broken ice. You can measure the altitude, or you don't care. So,
I'm sorry. Can you?
I mean, in the center of the ice sheet, it's
Yep.
only if you can only make the effective measurements when there is a broken ice.
Broken. Oh, for sea ice. Yeah. 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 No, that's right. It gets very hard in the wintertime in the center of our Arctic ice pack to do that. But you're going to just have to extrapolate to the closest leads, which will be, in some cases, a little bit removed, for sure.
Okay. Thanks.
And I think we got some online.
Oh, no.
Yes, so our first one is, are there any proposals for the replacement of IceBridge as of yet?
Not that I know of. That's a really good question. So the question was, they can hear your microphone, right? Yeah. So not that I know of yet. We haven't had that type of proposal call. The most recent ones are really associated with ICESat 2. I'm excited to see what happens. I also think the OMG campaign that I showed, the Bassler that drops the SONs into the fjords, that's a really big aircraft campaign in the polar regions. And I think polar science, we're going to have to wait our turn again to get another one like that. But no, not currently.
Okay, here's a big one. So second one, we have 3. So second one is, how do you measure ice age?
Oh, so that one was, it started with people literally just mapping parcels of ice and tracking them through space and time, that's why it was that's a really, really difficult thing to put together. And I don't know how they automated it, but there was some level of automation. But it was basically just mapping and following parcels of sea ice that they could identify. Sounds horrible. Yep.
Okay, last question. Is it possible to apply this to ice in the tropics, say in Peru?
Yeah, I think the problem there is, it absolutely is. The problem there, Peru is so close to the equator that our tracks get spread out a little bit. And in the mid-latitudes, first thing is we're not in a repeat track mode in the mid-latitudes. We do a cool off-pointing scenario to help the vegetation community and to sort of map the whole Earth with respect to our vegetation canopy. polar regions, we're in an exact repeat. In the mid-latitudes, we are not in a repeat. We're off pointing to mow the lawn to get as much data as possible. So in Peru, you're not going to get that exact repeat every single year. You'll get it starting in about 2.5 years of ICESat 2 data collection. So that's problem number one. Problem number two is, what is the trend of your glacier relative to the tracks of ICESat 2? Sometimes you get lucky, and the trend is either perfectly normal to the track, or being completely perpendicular to the track is good as well. But sometimes you're in that weird zone where it's not quite ideal for what you're trying to do. But we certainly, all those data are there. You can freely download them and see where they get you.
Thanks.
Thank you.
Okay, let's call on the next speaker.